Hello. We're going to do a little bit of heavy lifting, but there's good news in that it's very limited in scope. We're going to talk about how to find the center of mass of an object, either of an object with a uniform distribution of mass or non-uniform distribution of mass. And that's kind of the clincher, is doing the non-uniform ones using calculus. So to begin with, let's just kind of refresh from what we've seen earlier when we're talking about center of mass, and that's the center of mass is the formula for center of mass would be m1 times x1 plus m2 times x2 plus m3 times x3 all over the total mass would be m1 plus m2 plus m3. And a slightly, this could go on as many masses as you have. And a slightly more elegant way of representing this would be to say it is the sum of each mass. I don't remember what I is, infinite, some number of infinite number of masses at their infinite number of locations. But so the sum of each of those individual masses times their position divided by the sum of all of the little masses. And when we see sums, we should get our spidey senses tingling and start thinking calculus. That essentially means that what we want to do sort of conceptually is we want to add up the location of the center of mass of each of these little itty bitty tiny pieces divided by the mass of the sum of each of the little tiny itty bitty masses, and that should give us our center of mass. So how do we sort of turn this into calculus? And well, basically this is what it looks like. This is what becomes of the sum of the mass times the locations divided by the sum of the masses. So we get this integral, which at first glance looks very unfriendly. Well, I'll tell you a couple things. This may reassure you. Unlike most problems in physics where there are a lot of ways to go about doing a problem, a lot of different approaches and different formulas, the sort of good news as far as like AP curriculum goes is that there's really only one way to do this. This is the way. It's like playing a piece of music. This isn't jazz. We are playing it the way it's meant to be played. And here is the way it's meant to be played. So when it comes, test time or applications in the future in physics, as we'll see in rotational motion. This is sort of the part of the good news, bad news part. There's really only one way that you're going to be asked to do this. And so if you practice this way, you should succeed. And also, because the scope of these problems right now is very limited, that should hopefully give you a little bit of a foundation before we try something similar to this when we get into the rotational inertia, to more rotation-y stuff next unit. All right, so let's do this. So imagine that really what this is asking us to do, by this I mean the integral, it's asking us to add up all of these little itty bitty tiny pieces of mass at their respective locations. And so what that amounts to is dividing this long bar into itty bitty tiny slivers, each of which has a thickness dx. And of course, by virtue of the fact that it exists, it's got to have some mass. And so that piece of thickness dx has got to have some corresponding tiny little infinitesimally small dm. So each piece of thickness dx has a mass dm. And so then one question is, is there a relationship between them? And well, the answer is yes. What we're being told in this case is that it has a constant linear density. So every one of those pieces of thickness dx is going to have the same amount of mass as any other one. As you go from one end of the bar to another, each little piece is going to have the same mass. And so this linear density, which could be indicated as the mass per unit length, well, as we break up this length into little tiny slivers, each of which is a dx thickness, each little itty bitty tiny piece of mass divided by each little tiny piece of thickness dx is our linear mass density. It's how much mass is there per length. Well, each little tiny sliver has a certain amount of mass per that length. And that is a constant value in this case. It's constant. All right, so for the moment, we're just going to call it lambda. It's the Greek letter lambda. Whatever it is what it is. We don't know what the value of the constant is, but for now, we'll just leave it as it is. So I'm going to get rid of this and give us some space to work. Now, sort of as an aside, you may see this formula written, if you watch other videos or look in a book, you may see it written as the R center of mass is equal to the integral of R dm divided by dm. In this case, the R is simply indicating a radial distance away from some origin. And in our case, since we are locating our bar horizontally, orienting it horizontally, any radial distance is going to be measured in the x direction or have some x value of distance away from 0. And so we're just substituting x for r. If we had turned this bar on its end and oriented it vertically, we would just sub in y. We would find the center of mass in the y direction. So it's not a conceptual difference. It's just specifying the general equation, which usually is the r, center of mass, the radial distance away from 0. But now we're specifying a direction. We're going in the x direction. So let's put this to work. So we got the interest of finding the center of mass, and we've got this formula which we're growing to be a little more familiar with. It's the integral of x times dm divided by the integral of dm, which, if you think about it, if you take the integral of dm, well, you're adding up all the little tiny pieces of mass. Well, that kind of would be the total mass, wouldn't it? Yes, it would, which kind of works because that's how it works. Conceptually, anyway. Algebraically, calculusly, we have to pay more attention to what's going on. And here is the key element. I'm going to put a star next to this because this relationship unlocks the solution here. How so? How so? If lambda is equal to dm over dx. Now, if we look at this equation over here, we're trying to integrate a variable dx with respect to something that is not dx. We're trying to integrate x with respect to mass, which I'm not a calculus expert, but I don't feel like that's how you do it. And so how do you do it? Well, good thing we have a relationship between those two things. So I'm going to rearrange this. Multiply dx to both sides, which your calculus teacher won't like it. So dm is equal to lambda dx. This, maybe I'm going to double star this because this step is really what gets us the rest of the way there. Because now we can substitute that in for dm. then it becomes something we can actually integrate. So that gives us the integral of x times lambda dx over the integral, and we're going to substitute it in there too, over the integral of lambda times dx. Now, I wish I'd said this earlier. We're going to pause for a sec. Let's just visualize a uniform bar, a straight rod of, aluminum. Where do you think its center of mass would be? I mean, intuition tells me that it's going to be in the middle. Each of these little masses here is going to sort of offset, and each of the masses here is going to offset, and each of the masses here is going to offset, because it's equal. It's got equal density everywhere, and so if you sort of cancel out the pieces at the ends until you work all the way together, you're going to work together towards the center. You're going to end at the center. So intuition tells us that for a bar of length L, that the center mass should be 1/2 L. Let's keep that in mind. We feel like that should be true. Let's see if calculus tells us the same thing. Now, back to our integral. Since this bar goes from 0 to length L, we are going to evaluate our integrals from 0 to L, from 0 to L. You might be thinking, well, can I just cancel some things before I integrate? No. If you want to try that and then solve it out, you'll find that you don't get the same answer as what we're going to get. If you try two different ways and get different answers, they can't both be right. So I'll tell you in advance, canceling before integrating ain't right. So let's do what we can. So this lambda itself, since it is a constant linear density, that actually has a constant. We can pull that out front. So we got lambda times the integral from 0 to L of x dx divided by lambda over the integral from 0 to L of dx. Now the lambda has been pulled out of the integral. We're not integrating the lambda, so we actually can cancel that out because that's not inside the integral. Now we got to deal with what's inside the integral. X dx, the integral of that is going to be raised to the second power, so it's going to be x squared 1/2 x squared over the integral of dx is going to be x. And now that we've done the integration, now we can cancel some stuff out. Now, whatever we get after canceling, we're still going to evaluate from 0 to L. But now that we've done the integration, we can cancel some stuff. Well, x cancels with that squared, and so what we're left with is 1/2 x evaluated from 0 to L. We plug in L for x and 0 for x. Well, we get a final answer of 1/2 L. Isn't that nice? Satisfying. Now we're going to take this one, I don't want to say a step further. We're going to see another example, but this time an example where we do not have a constant linear density. We're going to have a linear density where lambda is 4x. Basically, like think of it like a linear equation, like y equals mx. As you get further along the x dimension, the density gets greater. In other words, there's going to be more mass further down the bar. It's like having a little tiny bit of mass. I'm going to start even more sparse than that. A little bit of tiny mass, and then as you get further down the bar gets denser and denser and denser. So clearly, the center of mass is not going to be in the physical center of the bar because there's way more mass over here than there is over here. If you tried to balance it there, it's going to tip over clockwise. So how do we deal with this? Exactly the same way we just did. We're going to conceptually break this into little pieces of thickness dx, each of which has a mass dm, and it turns out the ratio of mass per little tiny piece dx is not a constant. In this case, the linear density, the mass per length, mass per section, is going to be equal to 4x. It's nonlinear. It's not a constant value. It's not. It has a variable relationship. So just like we did before, we're going to rearrange this to solve for dm. This is the trick. Remember I said I double started before. Rearrange this to get dm equals 4x dx double star. Take your linear density, rearrange it to solve for dm, and that is going to set you free. So the center of mass is equal to x times dm over dm. But now we have an expression for dm. So that's going to be x times 4x dx. Slow down just a bit in my writing. 4x dx. I'm going to get mellow. Divided by the integral of 4x dx. Remember, don't forget that one because it's x times dm. This whole thing right here is just the dm. And each of those is being integrated from 0 to L, from 0 to L. So let's, we can't pull out the lambda. The lambda's not there anymore because lambda itself is a variable. So we can pull out constants though. 4, for example, is a constant. So we got 4 times the integral from 0 to L of x squared dx divided by 4 times the integral from 0 to L times x dx. Well, 4 cancels with 4. It simplifies it just a little bit. So now let's take the integrals. X squared integral is going to be 1/3 x cubed divided by the integral of x is going to be 1/2 x squared. And we're going to evaluate that from 0 to L. Now that we've done the integral, we can cancel some things. So x squared cancels 2 powers of that x. And what we're left with is 1/3 x divided by 1/2, evaluated from 0 to L. I can do this in whatever order. I'm going to rearrange. So dividing by 1/2 is the same thing as multiplying by 2. So that's 2/3 x evaluated from 0 to L. That's going to put the center mass at 2/3 L. That is where the center of mass of this bar is. We've got a bar with variable density, and it turns out that if we cut this bar into thirds, that's where this center mass is going to be. And we're going to see an interesting thing in class that this pertains to, and I'm going to sort of lead into it by saying, well, earlier on I said, what if we were to think of it like a linear equation? Well, if we had lambda versus x, that would be a linear equation. That would be a straight line. And if we stretch that out as far as L, then what we're essentially looking at is a triangle. And you might notice that the 4 didn't really show, like the 4 got canceled. What happened to the 4? Why doesn't the 4 matter? Well, it turns out the answer is no. The 4 doesn't matter. 1, mathematically, it canceled. Clearly, it doesn't matter. But really, all that 4 is telling us is the slope of this relationship, the slope of this lambda versus x graph. So we could have a really mellow one, or we could have a really steep one. But it turns out, if you do the geometry, just as well as doing calculus, that it doesn't matter the thickness or the height of the triangle. the center of mass of the triangle is still going to be at 2/3 L, no matter what. And if you were so inclined, you could redo this with any value of any coefficient for the x, get the same answer. So I know this is a bit of a lot to take in. Repeat. Do these on repeat. Do the same example 5 times so that the steps become habit. And again, unfortunately, I'm not the calculus expert, so your calc teacher can explain in much more detail why it works, and use the right math words. But as far as AP Physics goes, this is a skill that you're going to need, and we're going to see this kind of skill show up again when we get into rotational stuff. So try to get good at it right now. Put in the practice. It will pay off. Thanks, everybody.